was at Minnesota for freezing for many years, and now he's at USC in electrical and computer engineering. Works in all sorts of areas in network systems and distributed control. And look forward to hearing your work.
Thank you, Sean. Thanks for this kind of introduction and for your invitation to participate in this exciting workshop. So I'll be talking about convergence and sample complexity of gradient methods for the model-free linear quadratic regulator problem. And this is work done by my PhD student Hessam in collaboration with my former student and postdoc Armin and my friend and colleague Magdi at USC. So as all of you know, an important theme in this workshop is whether we can learn controllers potentially for complex dynamical systems that operate in uncertain environments in the absence of first principle models, perhaps by strategically using data that we have at our disposal. And obviously this is a challenging question, and in order to make some progress and to see how much mileage we can get, it is instructive actually to narrow scope a little bit and to perhaps examine standard problems that we know how to handle when we have models in the absence of models. So in view of that, I'm going to consider a classical problem in control theory that has 60-year-old history, namely the linear quadratic regulator problem. And this problem involves minimization of a quadratic cost for linear dynamical systems. And there are many different variations of the theme, and perhaps the simplest instance arises for linear time invariant dynamical systems that it involves quadratic costs that we want to minimize over an infinite horizon. Just for the sake of convenience and for personal taste, I'm going to focus on continuous time dynamical systems. Whatever I tell you today holds in discrete time as well. And the model is given by this first order vector valued ordinary differential equation that governs the evolution of the n-dimensional state vector x in the presence of a control input u and the random initial condition x naught whose distribution we assume to know. These matrices A and B are constant matrices for linear time invariant systems, and they determine model parameters. A is a dynamical generator, and matrix B tells us how control input enters into the state equation. And matrices Q and R are positive definite matrices that specify state and control weights. What I need to highlight is that minimization is done over all state and control trajectories, and the optimal solution is given by a linear feedback policy, namely at any time instant, at any t, you form optimal control action by acting on the vector of available state measurements by this fixed matrix K. And this fixed matrix can be obtained from a positive definite solution of a celebrated algebraic Riccati equation, and under mild system theoretic conditions, namely well-known controllability and observability requirements, there is a unique positive definite solution to this quadratic equation, which provides optimal stabilizing feedback gain that not only minimizes the quadratic cost for linear dynamical system, but also provides closed loop stability. And if you have a model, there are efficient linear algebraic and iterative techniques that you can utilize to compute solution to a Riccati equation. However, the challenge that arises is what to do in situations where you don't have model parameters, namely these matrices A and B. And perhaps one approach that you may want to utilize is to use strategically data to estimate matrices A and B, and then to proceed down the standard route. So the approach that we are going to take is slightly different. We are going to tap into the area of model-free reinforcement learning and to attempt to learn feedback policy by optimizing over feedback gain case. And you can easily express LQR cost in terms of the feedback gain matrix. And challenges that arise in this context is, first of all, to establish convergence properties. This is a challenging question because it is a standard fact that the LQR cost is a non-convex function of the feedback gain, and in the absence of models, you have also a burden to establish statistical properties, namely sample complexity of your gradient-based algorithms. And what I'm going to tell you in the next couple of slides is very briefly to list our contributions in this area, and the rest of my talk is going to be devoted to explaining essentially what we've done and comparing to the state of the art. So our first contribution is to show exponential stability over the set of stabilizing feedback gains for gradient flow dynamics for the linear quadratic regulator problem for continuous time systems. It is a little bit more convenient to work with differential equations than with recurrence relations, but it turns out that actually even gradient descent for continuous time LQR inherits property that we established for this ordinary differential equation. Namely, we can show linear convergence over the set of stabilizing feedback gains with a fixed step size alpha. So these results are relevant even in the context when you have your model, namely even when you have matrices A and B at your disposal. And I'll tell you essentially how we establish, give you at least a flavor of how we establish these properties. In the absence of models, what we've done, we proved linear convergence over the set of stabilizing feedback gains and established logarithmic complexity with respect to the reciprocal of the desired accuracy of the random search method for the linear quadratic regulator problem. And I'll be very specific what I mean by random search method. What I would like to highlight is that all of our results hold with high probability, and we do everything offline. So if you expect regret type bounds and results of that sort, none of that is going to be present in my talk today. And I would like to draw your attention to our archive post that has been also conditionally accepted for publication in IEEE transactions on automatic control. So the way I'm going to present my results, I'm going to start from the second result, because that's a topic that is of interest to this audience, and then if time permits, I'll go back to establishing properties of gradient flow dynamics. But before I do that, I would like just briefly to highlight key features that allow you to establish linear convergence of gradient descent in the absence of convexity. Namely, if you manage to show that your LQR cost possesses smoothness and gradient dominance properties over the its sublevel sets, then you can show actually linear convergence of gradient descent. And this is exactly what University of Washington group led by Mariam Fazel and co-workers has done a couple of years ago for the discrete time linear quadratic regulator. And we proved similar properties for the continuous time problem using completely different proof techniques, and that hopefully I'll get a chance to highlight in the second part of my talk. So let me start with the random search method for LQR, and highlight our results regarding convergence and sample complexity. The challenge that you are facing in the model-free setup is that you don't have access to true gradients. You can only access random function values, perhaps by running experiment or by tapping into simulation engine that domain experts have developed, and they're kind enough to allow you to run simulation in the presence of a certain feedback gain and certain initial condition, and you can obtain random function values, and then LQR objective is obtained by computing expectation over initial conditions that we assume to be zero mean unit variance with bounded sub-Gaussian norm. This slide summarizes what I mean by random search method for model-free LQR. It's essentially a technique that attempts to emulate properties of gradient descent by estimating gradient using random function values. And we tap into the area of derivative-free optimization to techniques that you may want to utilize are listed here. They're respectively given by 2 and 1 point gradient estimates. And if you take a look at these expressions, they may remind you of a standard central difference scheme from numerical analysis. The key difference between them is that in 2 point scheme, you assume that you can evaluate LQR cost at 2 different values of the feedback gain, but for the same initial condition. And this obviously clearly can be very restrictive assumption, especially in situations when you don't have simulation engine at your disposal, when you need to run experiments. But it is well known that 2 point schemes have better variance reducing properties relative to one-point schemes, where you assume that you can evaluate LQR cost at one value of the feedback gain for particular initial condition. So as you change feedback gain, you can only evaluate it for different initial conditions. So again, 2-point schemes have clear advantage, and I'll demonstrate this in a couple of minutes. So this approach here utilizes a single sample, but obviously nothing prevents you from running multiple simulations and using mini batch gradient estimate to form your search direction in the random search method. And the relevant question that arises here is how many samples you need in order to emulate properties of gradient descent, how long simulation time you should utilize, and what is the total number of iterations. So these three parameters essentially determine sample complexity of your model-free algorithm. And this is probably the most important slide in my talk. It summarizes our main result, in which we established that random search LQR that utilizes 2-point gradient estimate achieves a desired accuracy epsilon with high probability if the number of iterations is of order log of 1 over epsilon. Namely, if the number of iterations is of order that is logarithmic with respect to the reciprocal of the accuracy, and if the number of samples per iteration depends linearly on the state dimension, on the number of components in the state vector. Let's say if you have standard mechanical system, let's say mass spring damper system, your state vector would be containing 2 components, position and velocity perhaps of your mechanical system. If number of samples is linear in the problem dimension, then we have desired accuracy with high probability. And what I would like to highlight is that, in contrast to other results in the literature, number of samples does not depend on the desired accuracy. C is a constant here that depends on problem data, model parameters, but it does not depend on the desired accuracy, and sample complexity is obtained by multiplying these 2 numbers. So it's essentially linear in the problem dimension and logarithmic with respect to the reciprocal of the accuracy. So let me very briefly compare and contrast our results to state of the art in the literature. And what I would like to highlight is an impressive paper by UC Berkeley group, where they established sublinear convergence with polynomial sample complexity and decreasing step size using a single sample. And they clearly demonstrated advantages of 2-point schemes over 1-point gradient estimation schemes. And in addition to that, they show that if you have a luxury of using 1-point mini batch estimate with 1-point scheme, they confirmed essentially earlier result of University of Washington group, where you can actually establish linear convergence rate with a fixed step size, but with polynomial complexity. UC Berkeley group improved actually complexity bounds significantly relative to UW from 1 over epsilon to the 4th to 1 over epsilon to the squared, but still complexity that they established is polynomial with respect to the reciprocal of the desired accuracy. In our case, we have logarithmic complexity. And the question is, how do you establish these results? So what kind of approach do you need to use in your proof to establish results? One, perhaps natural avenue is to try to attempt gradient estimation error. And this is essentially what a standard technique would be. What I would like to highlight is that we don't do that. What we do, we exploit the problem structure and utilize results from non-asymptotic statistics to show that gradient estimate concentrates with high probability when projected to the direction of the gradient. Again, we don't attempt to control variance of the gradient estimation error as we approach optimal solution, but rather we just show that gradient estimate concentrates with high probability, and this allows us actually to improve bounds that have been established in the literature. So in our proof, we tap into standard results in optimization. We utilize approximate gradient descent, and it is standard fact that approximate gradient descent can converge with a fixed step size, provided that your direction has a projection that is big enough, and that its norm in the direction of the gradient, and that its norm does not become too large as measured by the norm of the gradient. And these two conditions hold in deterministic setup. These two parameters, theta 1 and theta 2, enter into a fixed step size in addition to smoothness parameter and PL type of a parameter. And both of them have interesting geometric interpretation that is, plotted here. Unfortunately, I don't have time to go into this. Rather than going into details, what I would like to highlight is that in our case, we need to establish actually that these two results hold with high probability. And this is actually what Hessa managed to prove. So rather than, again, providing technical details, what I would like to do is just to give you an example that illustrates perhaps flavor of our result. This is just a mechanical system that contains a number of inverted pendulum cards that are connected with masses and dampers, and each card is controlled by a force control, and you would like to design a model-free LQR around certain operating points. And what this slide shows is essentially, here we display histograms of these two expressions that I listed at a couple of slides ago, being equal to these values that are plotted along the horizontal axis. And if you choose these parameters theta 1 and theta 2 carefully with overwhelming probability, these two events are going to be satisfied. And convergence curves establish linear convergence without typical oscillations that you have in stochastic type of algorithms. So this was a very, very brief overview of what we've done in the area of model-free linear quadratic regulator. Again, for details, I would like to direct you to our paper. All of the details are contained there. But at this point, what I would like to do, I would like to switch gears a little bit and to go back to the setup when we have model, and to perhaps highlight what it takes to establish global exponential stability of the gradient flow dynamics for the LQR problem, even in the absence of convexity. And I feel that this part is perhaps going to be useful to outsiders, to controls community, because it's going to highlight some of the standard techniques that control theorists are familiar with, but that outside of CDC and ACC conferences that we go to are not that well known and well appreciated. So the first point that I would like to highlight is that as soon as you express LQR cost in terms of the feedback gain matrix, you lose convexity. And you need to trust me that you can write LQR cost over the set of stabilizing feedback gains using this expression here, where K is a feedback gain that you would like to design. Again, Q and R are state and control weights, and X is a closed loop covariance matrix of your state vector. So it turns out actually that you can write this matrix X in terms of the feedback gain K using this integral representation. And one reason why you don't have convexity is because in general, matrix exponential is not a convex function of its argument, of a feedback gain in this case. Another reason for loss of convexity is that set of stabilizing feedback gains is not a convex set. This is well known fact in control theory. So for at least two reasons, you don't have convexity of the LQR cost when you express it in terms of the feedback gain matrix. So what we want to do, we would like to analyze gradient flow and gradient descent dynamics and to establish its properties. So the question that arises is what is known about this problem? Even though it is non-convex, what kind of standard results can we tap into in order to make some progress? And again, I would like to highlight that global convergence properties for discrete time linear quadratic regulator problems were established by University of Washington group, and we've done similar things for both continuous time and discrete time using different proof techniques that I'm going to highlight right now. So what has been known for over 35 years is that in spite of lack of convexity, LQR cost has a unique critical point. And this unique critical point is given by the optimal solution that you can, when you have models, obtain from algebraic Riccati equation. Another interesting property is radial unboundedness of the LQR cost, namely, as you approach the boundary of the set of stabilizing feedback gains, or as your feedback gain shoots to infinity, your LQR cost blows up. And again, this has been known for a while. These two properties allow you actually to use objective error as a Lyapunov function for the gradient flow dynamics. Namely, it's trivial to show that if you utilize objective error, the difference between LQR cost and its optimal value, you can show that its derivative, dot here, represents derivative with respect to time along the solutions of the gradient flow dynamics is negative definite along the set of stabilizing feedback gains. And this is enough to establish asymptotic stability of the gradient flow dynamics over the set of stabilizing feedback gains. So asymptotic stability, global convergence to a unique critical point comes for free. It's literally a two-liner that taps into standard results that were established 35 years ago. All hard effort and heavy lifting has to be done to show rate of convergence, to establish exponential rate of convergence. And what I would like to remind you is that PL type of a condition allows you actually to relax strong convexity requirement on the objective function and to show linear convergence, so exponential convergence in the context of continuous time dynamical systems. If PL condition holds on the top of the requirements that I listed on the previous page, we can not only establish negative definiteness of the derivative of this Lyapunov function candidate along the solution of our system, but we can show that the bound is proportional to the Lyapunov function, where rho here is a PL parameter. And this is enough actually to show that you have exponential stability. And again, an example of a function that satisfies PL condition is given by a strongly convex objective function. Unfortunately, we don't even have convexity, let alone strong convexity, right? And the question is, how can we go about establishing that PL condition holds for the LQR cost? And the way we do this is very different from the approach that University of Washington group used. We actually utilize a standard convex re-parameterization from control theory and then go back to the original set of coordinates and establish relation between them. So let me just give you a flavor of how this is done. You need to trust me that you can write linear quadratic regulator problem as listed here, namely LQR cost that I listed a couple of slides ago. We would like to minimize it with respect to feedback gain matrix K and this covariance matrix X under the following two constraints. Positive definiteness of the covariance matrix is equivalent and guarantees closed loop stability, stability of your controlled system. And this equation here is a Lyapunov equation, standard equation in control theory, that tells you how closed loop covariance matrix is related to your feedback gain and to your model parameters. So any student of optimization would immediately recognize that this is quadratic equation in your optimization variables. And as you know, quadratic convex optimization does not tolerate quadratic equality constraints. We need to have linear equality constraint in order to have convex problems. So, however, optimization variables enter into your quadratic equality constraint in a convenient way. And if you stare at this equation long enough, you may notice that if you introduce change of variables, if you introduce new variable y, which is given by a product of the feedback gain k and covariance matrix x, this quadratic equality constraint is going to become linear constraint now in variables x and y. And this variable y has the same number of rows and columns as the feedback gain matrix, and under closed loop stability, you can go back and forth between y and k without any loss of information. And it turns out actually that you can rewrite now your problem in the following form. This problem turns out to be jointly convex in variables x and y. Your quadratic equality constraint has become linear, and what control theorists would typically do, we would utilize Schur complement here to bring it into semi-definite programming characterization, which is dual essentially to the algebraic Riccati equation. This is not what we do here. Our approach is to express covariance matrix in terms of this new matrix Y, and you can do that and express actually covariance matrix as an affine function of this matrix Y, where these calligraphic symbols A and B are linear operators that are listed here. And once you do that, you can write f of k as a convex function of this new variable Y, which again has the same number of rows and columns as your feedback gain matrix K. Very good. So you have convexity new variables, right? And now if you're happy with working in Y coordinates, then you need to study gradient flow in Y coordinates over the convex landscape. In addition to convexity, actually, it turns out that you have strong convexity over the sub-level sets of the LQR cost in this new set of coordinates, right? Hessam very skillfully managed to show that in addition to convexity, we have strong convexity where this set here is nothing but a sub-level set over the set of stabilizing matrices Y. If you want to, in these new coordinates, once you have strong convexity, all results come for free because PL condition is immediately satisfied, and you can essentially establish exponential stability without any issues. And this is exactly what we've done in our paper. We established exponential stability over the set of stabilizing, if you want to, matrices Y naught of the corresponding gradient flow dynamics. This is very nice, very elegant. However, it doesn't tell us anything about the property of the gradient flow dynamics in the original coordinates, right? And since I was instructed to speak for 25 minutes and I'm already at 26, I'm not going to have a chance to go into details, but what I want to advertise essentially is that if you take a look at our paper, we established very nice relation between gradient flow dynamics over this convex landscape to the gradient flow dynamics over non-convex landscape, using geometric relation between these matrices Y and K, and some additional techniques that are pretty standard in optimization, and that allow us to establish these strong properties. Again, I don't have time to go through these details. I felt that this is way more closer to the background of the audience, but perhaps this change of variables was a new aspect that outsiders to controls community haven't seen before. And again, this is very different from a proof technique that University of Washington group use. With this, I'd like to wrap up my talk by telling you that there are lots of additional challenges in this rapidly evolving landscape, and the problem that is of interest to me personally is a structured feedback synthesis, perhaps for the purpose of designing distributed controllers, where control action is formed by utilizing limited information exchange between different subsystems. And this turns out to be a very, very interesting problem, because the standard change of variables that I utilized a few slides ago is no longer enough to bring you into convex parameterization. The reason being that arbitrary sparsity pattern on K does not easily translate into sparsity patterns on X and Y. And if you stare enough at these expressions here, you'll quickly realize that this is the case. So standard change of variables does not work. So there are interesting questions even when you have models and obviously output feedback reinforcement learning, where you don't have a luxury of having access to state measurements, but rather just to noisy output measurements is a big challenge for reinforcement learning. With this, I'd like to list references that have been useful to us and our own papers. In addition to the paper that I mentioned, archive post, we also extended all of these results to a discrete time case, and this was already published in Control Systems Letters. So the most important slide, I'd like to thank Hessam for his hard and brilliant work, and Armin and Magdi for being outstanding collaborators, and of course sources of funding, Air Force Office of Scientific Research and National Science Foundation. Thank you.
Bravo, that's wonderful work. So let's have a question or two and then go straight to the panel, right? Have I screwed up the schedule? We have a break, I'm sorry. Oh, that's right, it's not till the end. Excuse me, I got myself flustered. So a quick question before the break, anybody?
Yeah, I wanted to ask you about the discrete time. Is there a nice and elegant way of transporting the continuous time results to discrete time? I wish there was.
Unfortunately, geometry in discrete time case is different. But all of these, if you take a look at this formulation here, what would be different is that Lyapunov equation has different form. But there is an equivalent convex re-parameterization even in discrete time case. And whatever we presented in continuous time carries over actually to discrete time. If your question was, if we start with discrete time dynamics, do these results extend? They do. If your question was, if instead of gradient flow dynamics, I utilize gradient descent, the answer is again affirmative. Right? We showed actually that with a fixed step size, forward Euler discretization essentially of a gradient flow dynamics has linear convergence. So answer is yes to both questions. Unfortunately, you would have to get familiar with the geometry in discrete time case if you're familiar with continuous time, and there is no free lunch there, even for experts. Control theorists, this does not come for free.
Yeah, I was hoping for a free lunch. But...
Unfortunately, no. Even we have preferences in terms of continuous time folks versus discrete time, and this is very often for whatever you become comfortable with first. And unfortunately, in discrete time, there are some additional things that you need to pay attention. But good news is that everything extends. So I can provide additional details if you're interested, and provide pointers to the literature as well.
Yeah, thanks.
Yeah. It's amazing how nice this is. I mean, considering how ugly Q-learning is for LQR and how elegant this is, it's really, really surprising. It's,
I'll just smile and plead the fifth.
Yeah, okay. Anything else out there? Because we could chat for 20 minutes, so we can have a break. Yeah. So.
Okay. Thank you, guys.
Okay, so so anyway, so we'll be back in 25 minutes for our next talk, and then right after that will be a panel. Okay, ciao.
Thanks, Sean.